This is our second video in our unit on probability and counting, and today we are going to be introducing probability. This first video will look at the definition of probability, and the next video will look at probability of complementary events, and then finally we'll have some extra examples. To get started, the what of today's lesson, we are going to determine sample spaces for events and the probability of some dependent events, as well as complements, and just basic simple probability. The why. So probability is the basis for the entire field of statistics and data analysis. So it's incredibly important, although we will not get nearly as far as what you would see in a statistics class. We will be laying some of the foundation. And if you find this interesting, I really encourage you to take a statistics class later on. So we need to start with some preliminary vocabulary. Namely 4 terms: experiment, outcome, sample space, and event. Yeah, that's the only 4 there are. So an experiment is a situation with uncertain outcomes. So flipping a coin would be considered an experiment because until we get an outcome, we don't know what's going to happen. An outcome is a possible result of the experiment. So for the experiment of flipping a coin, the possible outcomes are heads or tails. A sample space is the set of all possible outcomes of an experiment. So the set of heads and tails is the sample space for flipping a coin. And an event is a subcollection of the sample space, which is some, but maybe not all outcomes. So getting heads would be a subspace, an event within that sample space of heads or tails. An event can be the entire sample space. So we could have an event getting either heads or tails. That isn't a particularly interesting event. We know one of those 2 things is going to happen, but it still is a valid event. So to define probability itself, we first need to define a sample space. So the sample space, remembering that definition we just had, the sample space is the set of every way all possible outcomes could occur. So note that outcomes may be repeated in the sample space if the same outcome can happen in multiple ways. The event is the set of every way a specific outcome could occur. So these definitions are just building slightly on the definitions on this last slide, but they're building toward a specific definition, namely set notation. In that if we think of sets as collections of objects, we can count the sizes of those sets. So that is what we are going to do in order to define probability. So we're going to let E be an event, a set, and S, the sample space, another set. So both of these are collections of things. N of E is the number of outcomes in which an event occurs. So how many things are in this set? And N of S is the number of outcomes in the sample space. So how many things are there? So the probability of an event is defined as the probability of E is equal to the ratio of the number of events in the event space divided by the number of events in the sample space. So we're calculating numbers and finding a ratio. So let's do some examples. A 20-sided die is rolled. We want to list the sample space. So a die with 20 sides has the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So the size of our sample space is going to be 20. Getting a number divisible by 3 is the event. So 3, 6, 9, 12, 15, and 18 are the only numbers from 1 through 20 that are divisible by 3. And so the size of our event space is going to be 1, 2, 3, 4, 5, 6. And so the probability that we get a number divisible by 3 is going to be 6 out of 20, which can be reduced to 3/10. And we can leave this as a fraction, or if you want to express it as a decimal, 0.3, or a percent, 30%. Generally, if we can express it as a percent or a finite decimal that doesn't go on forever, we can do so. Otherwise, we should keep it as a fraction. How about a two-sided dice? Two 10-sided dice are rolled and the numbers are added. So in this case, we have a first die and then a second die. And we need to think of their sum. So we have the numbers 1, 2, 3, 4, 5, 6, 7. Ooh, I need to go a little bit bigger. Or let me just erase some of these. I'll smush them closer together. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. And then our second dice, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So now that I've accounted for both die, I can make the sum. Let me change my line thickness for a moment though. So we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then we have 2, 4, 6. Hold on, I'm suddenly multiplying, but I should still be adding. So let me go back a couple terms. So 2 and 2 is 4. 2 and 1, hold on, I need to go even further back. This is why it helps to pay attention. I am finding their sums. So 2 and 1 is 3. Then 2 and 2 is 4. 2 and 3 is 5. Then 6, 7, 8, 9, 10, 11, 12. And we could continue this all the way. So I'm going to add some dots all the way to the last row. So 10 plus 1 is 11, then 12, 13, 14, 15, 16, 17, 18, 19, and 10 plus 10 is 20. So this is a visual depiction of the entire sample space. Notice that some numbers, 3, 4, 5, 11, appear more than once on this table. So labeling it like this, even though we have some dots, we've established the pattern for the whole table, for the whole sample space. So we want the sum greater than 50. So notice that the biggest number in this table is 20. Hold on, there's one last thing I forgot. We need to actually compute the size of our sample space. Notice that with 2 dice, we get a table with 100 entries. So the size of our sample space is 100. A sum greater than 50, well, the biggest number is 20. So this is an empty set. The size of our event is therefore 0. There are no possible outcomes where when we add a number between 1 and 10 with another number between 1 and 10, that we get a number bigger than 50. So the probability of getting a number greater than 50 is 0 out of 100, or just 0. Let's do 2 more examples. So a random day in 2021 is picked. There are 365 days in the year, going from January 1st to December 31st. So the size of our, interesting, the size of our sample space is equal to 365. Now, the first or last day of the month, we could certainly make a list of this, but if we're trying to get the probability, realizing that every month has a first and a last day, the size of our sample space, the size of our event space is going to be 24. 1 from each month at the beginning, 1 from each month at the end. And so the probability of randomly selecting the first or last day of the month would be 24 out of 365. Now, this is something we would call a compound event because 2 different things are happening. A coin is flipped and a day of the week is chosen. So we have our coin options, which could be heads or tails. And then we have our day option. So it could be Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. Sometimes we do Tuesday as TU and Thursday as TH. Other times you just put H for Thursday. So we could have a combination of heads on Sunday, tails on Sunday, heads on Monday, tails on Monday, all the way down to Saturday. I should be consistent. This would be heads on a Saturday or tails on a Saturday. So once again, we're just filling in enough to establish the whole pattern. Additionally, we can see that the size of our sample space is going to be 14. This is actually a result of the fundamental counting principle. Flipping a coin, picking a day of the week are independent. And so we have 2 options and 7 options. So we multiply the number of options together, we get 14. So getting a weekend or getting heads. So I'm going to highlight all of the ones that have a weekend or a head. So there's this one, this one, this one. If we were to continue down the line, we would have all of the ones for heads that we didn't write, plus the 2 for Saturday, which is a weekend. Because this says or, as long as one of those things is true, it's still true. So if we come back to our pen, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So the size of our event is 9. Whoops, forgot the equal sign. And so the probability of randomly getting a weekend or heads would be 9 over 14. There we go. So there's one more thing that I want to say about probability. So we're actually going to go back to this slide, because probability has some bounds. And so it's important to discuss what those are and what they mean. So if we think about the size, an event size, as we've seen in some of our example, the event could be equal to 0. And although we didn't see an example of this specifically, an event could also be equal to the entire sample space. That would be like flipping a coin and getting heads or tails. One of those is going to happen. So that would be everything. So we end up that probability, if we divide everything by the size of the sample space, we end up with 0 is less than or equal to the probability of an event. That's our size of the event space divided by the size of the sample space is less than or equal to 1. And so 0 means the probability the event is impossible. It's never going to happen. Probability of 1 is absolutely certain it will definitely happen. You can also express these as percents. So 0% to 100%. So that's why in the examples we just did a moment ago, all of our probabilities were between 0 and 1 or 0 and 100%. So keeping this in mind can help us identify possible mistakes. For example, if we get a probability that's negative or a probability that's greater than 1, we should say, hold on a second, something's wrong. I need to go back and fix this. So remembering this fact about probability is useful and important. And with that, we will take a break, come back with another video on the complements of events, and then we'll proceed with the remainder of our lesson.